What specific problem does the proposed method aim to solve in the context of explainability in deep learning models?
The proposed method aims to solve the problem of understanding the decision-making process of deep learning models by providing explanations that are more interpretable and meaningful. Specifically, the method addresses the challenges of consistency, entanglement, and spatial dependence of concept vectors in concept-based explanation methods like concept activation vectors, CAVs. These properties impact the reliability and accuracy of model explanations, affecting the transparency and trustworthiness of the model's decision-making process. By analyzing and addressing these properties, the method aims to improve the interpretability of deep learning models, allowing for better understanding of model behavior and limitations.
How does the proposed method of concept activation vectors, CAVs, work, step by step?
Concept activation vectors, CAVs, are a method used to explain the decision-making process of deep learning models. To create a CAV for a concept, a probe dataset containing positive and negative samples related to the concept is needed. The activations in a specific layer of a neural network are then extracted for these samples. A binary linear classifier is trained to distinguish between the positive and negative activations, resulting in a normal vector, v_CL, that represents the concept in the activation space of that layer. The CAV captures how the model is sensitive to the concept in that specific layer. The sensitivity of the model to the concept across different classes is measured using testing with CAVs, TCAV scores, which indicate the fraction of inputs belonging to a class that are positively influenced by the concept. A statistical test is then used to determine the significance of the concept's influence on the model's output. The CAVs are used to provide high-level explanations using terms familiar to humans, helping to understand how the model works in a more interpretable way.
What are the theoretical or practical benefits of using concept-based methods like CAVs compared to low-level feature explainability methods?
The theoretical benefit of using concept-based methods like concept activation vectors, CAVs, compared to low-level feature explainability methods is that CAVs provide explanations using high-level terms that humans are familiar with, making it easier to interpret and understand model decisions. CAVs help in addressing the challenges faced by low-level feature methods, such as confirmation bias and lack of faithfulness. They offer insights into network representations and the meaning encoded by concept vectors. Additionally, CAVs allow for the analysis of properties like consistency across layers, entanglement of concepts, and spatial dependence, providing a deeper understanding of model behavior. Practically, CAVs offer a more intuitive and human-interpretable way of explaining model decisions, which is crucial for real-world applications where transparency and interpretability are essential. By focusing on high-level concepts, CAVs can help in debugging models, understanding their limitations, and improving model performance. They also provide tools to analyze and visualize properties like consistency, entanglement, and spatial dependence, enabling practitioners to make informed decisions about model behavior. Overall, CAVs offer a more holistic and meaningful explanation of model decisions compared to low-level feature methods, enhancing the trust and usability of deep learning models in various domains.
How is the concept of consistency across layers explored and validated in the paper?
The concept of consistency across layers is explored and validated in the paper by introducing the hypothesis of consistent concept vectors across layers, NH1. The paper defines consistency as the ability of two concept vectors found in different layers to have the same downstream effect on the model when activations are perturbed in their direction. The null hypothesis, NH1, states that concept vector representations are consistent across layers. To validate this hypothesis, the paper conducts experiments using CAVs on the elements and ImageNet datasets. The paper measures the consistency of two perturbations using the consistency error metric, where a lower error indicates a higher level of consistency. The experiments include benchmarks such as optimized CAV, projected CAV, and random CAVs to provide context for the results. The results show that concept vectors found in different layers are not consistent, as indicated by the non-zero consistency error. This suggests that the directions encoded by CAVs in different layers are not equivalent, leading to varying TCAV scores across layers. The inability to find consistent concept vectors across layers implies that different layers represent different components of the same concept, impacting the model's behavior and decision-making process.
What limitations or challenges are associated with the concept entanglement hypothesis discussed in the paper?
The limitations associated with the concept entanglement hypothesis discussed in the paper include the challenge of identifying and separating the model's sensitivity to one concept from its sensitivity to related concepts. The paper highlights that if concepts are entangled, it becomes difficult to distinguish the effect of one concept from another when measuring the TCAV score. This means that when evaluating the impact of a specific concept, the presence of related concepts can lead to misleading explanations. The entanglement of concepts can result in TCAV scores that do not accurately reflect the model's sensitivity to individual concepts, as the effects of intertwined concepts may be inadvertently incorporated into the analysis. Additionally, the paper mentions that entangled concepts can complicate the interpretation of TCAV scores, potentially leading to incorrect conclusions about the model's behavior. Therefore, the entanglement of concepts poses a challenge in accurately assessing the model's sensitivity to specific concepts and can introduce ambiguity in the interpretation of TCAV results.
What future research directions or extensions are suggested by the authors to enhance the method of concept activation vectors, CAVs?
The authors suggest several future research directions or extensions to enhance the method of concept activation vectors, CAVs. Firstly, they recommend creating CAVs for multiple layers instead of just a single layer to better understand model behavior and ensure consistency across layers. Secondly, they propose verifying expected dependencies between related concepts to address concept entanglement issues. By being mindful that a positive TCAV score may be due to concept entanglement, researchers can improve the accuracy of their interpretations. Lastly, the authors suggest visualizing concept vector spatial dependence using spatial norms to explore the influence of spatial dependence on concepts. By analyzing spatial norms, researchers can gain insights into how the model's sensitivity to concepts may vary based on their locations in the input image. These recommendations aim to enhance the robustness and interpretability of the CAV method, providing a more comprehensive understanding of model behavior and concept representations.